We can see the universe with extraordinary clarity. 13.8 billion years of cosmic history mapped with precision instruments, expansion rates measured to fractions of a percent, the chemical composition of distant stars decoded from spectral lines, the temperature of space itself recorded to 5 decimal places. Modern cosmology rests on measurement. Within its tested regime, our models achieve remarkable precision. This is the oldest light in the universe. Radiation released when the cosmos was 380,000 years old. We have photographed it, analyzed its temperature fluctuations, traced the pattern of density variations that would eventually collapse into galaxies. We can rewind further still. Before the first atoms formed, there was plasma, hydrogen and helium nuclei suspended in a sea of electrons, photons scattering endlessly. We understand this era with high confidence. The physics is confirmed by particle accelerators. Before that, the synthesis of light elements, protons fusing into helium nuclei in the first 3 minutes. We have measured the abundance of these elements across the observable universe. The predictions match reality. We can trace cosmic evolution back to 1 second after expansion began, to 1/1,000,000th of a second, to 1/1,000,000,000th of a second, and possibly, though with considerably less certainty, to a brief window around 10 to the -36th of a second, when space itself may have undergone exponential expansion. For much of this, we have well-tested equations. For much of this, our physical frameworks prove reliable. And then, at approximately 10 to the -44th of a second, our current physical frameworks reach their limit. Not because reality ends, because our description of it does. This is a documentary about a boundary, the most profound boundary in science. Not the edge of the universe, but the edge of what we can currently know about it. Begin with certainty. In 1929, Edwin Hubble discovered that distant galaxies are receding from us. The farther away they are, the faster they move. This was the first empirical evidence that the universe is expanding. Not expanding into anything, space itself is stretching. The distances between galaxy clusters grow larger over time. If this is true now, it was denser in the past. Rewind the expansion and the universe converges toward a hot, compressed state. Since Hubble, measurements have become astonishingly precise. The Hubble constant, the rate of expansion, is now constrained to better than a few percent accuracy, though tension remains between different measurement methods. Current estimates place it at approximately 67 to 73 kilometers per second per megaparsec. The universe expands. This is supported by multiple independent lines of evidence. The standard cosmological model, lambda cold dark matter, or lambda CDM, describes cosmic evolution with extraordinary success. Dark energy and cold dark matter are inferred components needed to explain observations. Dark energy drives acceleration. Cold dark matter provides gravitational scaffolding. Ordinary matter, everything we can directly detect, comprises less than 5% of the total. This model allows us to reconstruct history. 4.6 billion years ago, the sun ignites. Hundreds of millions of years after expansion began, the first stars fuse hydrogen into heavier elements. 380,000 years, electrons combine with nuclei. The universe becomes transparent. Light travels freely for the first time. Before that lies the era of nucleosynthesis. Between 1 and 3 minutes after expansion began, the universe was a nuclear furnace. Protons fused into deuterium, deuterium into helium-3, helium-3 into helium-4, trace amounts of lithium. We can measure the abundance of these elements throughout the cosmos. Approximately 75% hydrogen, 25% helium by mass. These ratios match theoretical predictions with remarkable precision. This is cosmology confirmed by chemistry. And then there is the microwave background itself. Predicted in 1948 by George Gamow, Ralph Alpher, and Robert Herman, discovered accidentally in 1965 by Arno Penzias and Robert Wilson, background noise in a radio antenna, uniform in every direction. mapped with increasing precision by 3 generations of satellites: COBE in 1989, WMAP in 2001, Planck in 2013. The temperature variations are minuscule, 1 part in 100,000, but encoded within them is the structure of the early universe, density fluctuations that would later collapse under gravity to form galaxies, clusters, superclusters. We can see the same patterns imprinted in the large-scale distribution of galaxies today. Sound waves frozen into cosmic structure, predicted, measured, confirmed. The early universe yields to physics we can test. But this raises a question. If we can measure the universe at 380,000 years, if we can model it reliably back to the first few minutes, how much further can we actually go? 1 second after expansion began, the temperature of the universe was approximately 10 billion Kelvin, hot enough to prevent the formation of atomic nuclei. Protons and neutrons swam freely in a plasma of electrons, photons, and neutrinos. We understand this regime with substantial confidence. Particle physics has been tested at these energy scales in accelerators. The standard model predicts behavior accurately within this domain. At 1/10,000th of a second, quarks had not yet bound into protons and neutrons. The universe was a quark-gluon plasma, elementary particles in thermal equilibrium. This phase has been reproduced experimentally at RHIC and the LHC by colliding heavy ions at relativistic speeds. Earlier still, at 1/1,000,000th of a second, temperatures exceeded 1 trillion Kelvin. The strong nuclear force, mediated by gluons, held quarks in a collective fluid state. At approximately 1 trillionth of a second, 10 to the minus 12 seconds, something profound occurred. The electromagnetic force and the weak nuclear force were not yet distinct. They existed as a unified electro-weak interaction. As the universe cooled below a threshold energy of roughly 100 gigaelectron volts, this symmetry broke. The photon remained massless. The W and Z bosons acquired mass through the Higgs mechanism. This transition has been confirmed indirectly. The Higgs boson itself was detected at the Large Hadron Collider in 2012, validating the theoretical framework. We are now within the first trillionth of a second. Our confidence decreases, not because the mathematics fails, but because we cannot recreate these conditions experimentally. We move from tested physics to extrapolated physics. Between 10 to the minus 34th and 10 to the minus 36th seconds, some models propose grand unification. The strong, weak, and electromagnetic forces merge into a single interaction. This remains speculative. No evidence confirms it. But within this narrow time window, an idea emerged that would reshape cosmology. The horizon problem. The cosmic microwave background is remarkably uniform. Regions of sky separated by more than 1 degree have nearly identical temperatures, to within 1 part in 100,000. Yet according to standard expansion, these regions were never in causal contact. Light had not had time to travel between them. Information could not have been exchanged. How then did they reach thermal equilibrium? The flatness problem compounds this puzzle. The universe is spatially flat, or extremely close to it. Curvature measurements indicate we are within 1% of the critical density that separates positive from negative curvature. But flatness is an unstable equilibrium. Any slight deviation in the early universe would have amplified exponentially over time. For the cosmos to remain this flat today, initial conditions would have needed fine-tuning to extraordinary precision, at least within standard Big Bang cosmology. Two problems, both pointing toward the same narrow time window, both suggesting something happened before the hot Big Bang we observe. In 1980, physicist Ellen Guth proposed a solution: inflation. For an extraordinarily brief interval, possibly as short as 10 to the minus 36 seconds to 10 to the minus 34 seconds, space underwent exponential expansion. Not gradual stretching, but explosive doubling. Every fraction of a second at this scale, distances doubled, doubled again, perhaps 60 or 70 times in rapid succession. This would address both problems. Before inflation, the observable universe occupied a region small enough to have reached thermal equilibrium. Expansion then stretched this uniform patch to scales far larger than the observable cosmos today. What we see as causally disconnected regions were once in contact, and any initial curvature was flattened by the exponential expansion, the same way inflating a balloon smooths out wrinkles on its surface. The mechanism driving inflation is a hypothetical scalar field, the inflaton. Like the Higgs field, it permeates space. Unlike the Higgs, it carries energy in a false vacuum state. As the field slowly rolled down its potential energy curve, the vacuum energy remained nearly constant. This created negative pressure, a repulsive gravitational effect that drove exponential expansion. Eventually, the field reached the minimum of its potential. It oscillated, decayed into particles, and reheated the universe. Standard hot Big Bang cosmology resumed. Inflation is not directly observed, but it makes predictions that can be tested. Quantum fluctuations in the inflaton field would have been stretched to cosmic scales, seeding the density variations that became galaxies. These fluctuations should produce a specific statistical pattern in the CMB. The observations are consistent with this prediction. The scale invariance, the Gaussian distribution, the acoustic peak structure, all compatible with inflationary models, though not uniquely so. Inflation should also have produced gravitational waves. These would leave a distinct signature in the polarization of the microwave background, so-called B-mode patterns. In 2014, the BICEP-2 experiment announced detection of B-modes. The claim was later retracted. The signal came from galactic dust, not primordial gravitational waves. The direct evidence remains elusive. Inflation is not proven. It is the leading framework, mathematically elegant, empirically consistent in some respects, but not yet confirmed at a fundamental level. And there is no consensus on what the inflaton field actually is. Dozens of models exist, each with different potential energy curves, different predictions for observables. Some versions of inflation are eternal, producing an infinite number of bubble universes with varying physical constants. This is intellectually provocative, but empirically untestable. Even if inflation occurred, it does not answer the deeper question. What powered it? What determined the inflaton's initial conditions? And before inflation itself, what happened in the first fraction of a second? General relativity describes gravity as the curvature of spacetime. Mass and energy warp the fabric of the cosmos. Objects follow geodesics, the straightest possible paths, through curved geometry. This theory has been tested exhaustively within its regime. Gravitational lensing, perihelion precession of Mercury, gravitational time dilation, the detection of gravitational waves from merging black holes. Within the domains where we can test it, Einstein's framework succeeds. Quantum field theory describes the behavior of particles and forces at subatomic scales. Matter is not composed of fixed objects, but of excitations in underlying fields. Photons are ripples in the electromagnetic field. Electrons are excitations in the electron field. Quarks, gluons, neutrinos, all manifestations of quantum fields permeating space-time. The Standard Model predicts phenomena with extraordinary accuracy. The magnetic moment of the electron, for instance, is measured and calculated to better than 1 part in a trillion. Within its tested domain, quantum field theory achieves remarkable precision. But these two theories, general relativity and quantum field theory, are incompatible at extreme scales. Not wrong, incompatible. General relativity treats spacetime as a smooth continuum. Quantum field theory requires fixed background geometry. GR describes large-scale structure. QFT describes microscopic interactions. At everyday scales, the two domains do not overlap, but at extreme conditions, extraordinarily high energy densities compressed into extraordinarily small regions, both theories apply simultaneously, and they give contradictory answers. There exists a natural scale where this incompatibility becomes unavoidable. The Planck Scale, defined not by arbitrary human units, but by the fundamental constants of nature. The speed of light, circa, Newton's gravitational constant, g, Planck's constant, h bar, Planck length, roughly 10 to the minus 35 meters, 20 orders of magnitude smaller than a proton. Planck time, roughly 10 to the minus 44 seconds, the time it would take light to travel 1 Planck length. Planck temperature, roughly 10 to the 32 Kelvin, 100 million trillion times hotter than the core of the Sun. At these scales, the gravitational field fluctuates quantum mechanically. Space-time itself becomes uncertain, not a smooth stage on which particles move, but a roiling foam of geometry undergoing constant creation and annihilation, or so some theoretical approaches suggest. This is where our current physics reaches its limit. When physicists solve Einstein's field equations for a collapsing star, the mathematics predicts a singularity, a point of infinite density, infinite curvature, infinite temperature. Rewind the expanding universe using general relativity alone, and the same result appears. All matter, all energy, all space-time compressed into a singular point at time zero. But many physicists suspect this singularity is not real. Infinities in physics are typically signals of theory failure. They indicate the equations have been pushed beyond their domain of validity. General relativity does not include quantum mechanics. It treats matter and energy as continuous. At Planck scale densities, this assumption breaks down. The singularity is not a confirmed object. It is a mathematical boundary marking where our current description fails. This tension appears elsewhere. Black hole thermodynamics suggests information is lost when matter crosses an event horizon, violating quantum mechanical principles. The information paradox remains unresolved. Stephen Hawking showed that black holes should emit radiation due to quantum effects near the horizon. This implies they eventually evaporate, another phenomenon requiring both GR and QFT, but for which no complete theory exists. For more than 4 decades, physicists have sought a unified theory, a quantum theory of gravity. We stand at a conceptual wall, not because reality becomes infinite or paradoxical, but because the mathematics we use to describe reality stops making consistent predictions. If we rewind the cosmos to the Planck time, we encountered this wall directly. Before approximately 10 to the minus 44 seconds, the energy density of the universe was so extreme that quantum gravitational effects would have dominated. Classical space-time may not have existed in any meaningful sense, though what this means physically remains an open theoretical question. What this means for reality itself, we cannot say with certainty. Not because we lack imagination, because we lack a tested mathematical framework. And yet, physics has never stopped at a boundary before. Every era of physics has encountered limits, and nearly every time, those limits dissolved when a deeper theory emerged. In the 17th century, Isaac Newton unified celestial and terrestrial motion with a single law of gravity. For 2 centuries, Newtonian mechanics appeared complete. Then, astronomers noticed Mercury's orbit was wrong. A tiny discrepancy, 43 arcseconds per century, that Newton's law could not explain. In 1915, Einstein replaced Newton's gravity with general relativity. Space-time curvature predicted Mercury's orbit exactly. The boundary receded. At the turn of the 20th century, classical physics could not explain the spectrum of light emitted by heated objects. Existing theory predicted infinite energy at short wavelengths, the ultraviolet catastrophe. Max Planck resolved the paradox by introducing quantized energy levels. Energy was absorbed and emitted in discrete packets, quanta. The boundary receded. Quantum mechanics explained atomic structure, chemical bonding, the stability of matter. What had seemed fundamentally mysterious became calculable. Quantum field theory unified electromagnetism with the weak nuclear force. The Standard Model emerged, a framework describing all known particles and 3 of the 4 fundamental forces. Cosmology transformed from philosophy into empirical science. The cosmic microwave background was predicted, discovered, mapped. Gravitational waves, predicted by Einstein a century ago, were detected in 2015. Each time physics reached a wall, mathematics found a door. But history does not guarantee repetition. The Planck scale may be different, or it may not. String theory proposes that the fundamental constituents of reality are not point particles, but one-dimensional objects, strings. Each vibrational mode corresponds to a different particle. An electron is a string vibrating one way, a quark vibrates another. A graviton, the hypothetical quantum of gravity, emerges naturally from the mathematics. The theory requires additional spatial dimensions beyond the 3 we experience. Depending on the version, either 10 or 11 total dimensions. The extra dimensions are compactified, curled up at scales far too small to detect. Some versions describe our universe as a 3-dimensional membrane, or brain, embedded in higher dimensional space. The Big Bang might have been a collision between brains. Others propose a pre-Big Bang phase. The universe existed in a different state before the expansion we observe. String gas cosmology suggests a long period of contraction preceded the hot Big Bang. The mathematics of string theory is extraordinarily rich, but it is also extraordinarily flexible. Estimates suggest an enormous number of possible vacuum configurations, each corresponding to a different set of physical laws. And no direct experimental evidence supports any of it. String theory makes predictions only at the Planck scale. Current particle accelerators reach energies around 10 to the 4th giga-electron-volts. The Planck energy is 10 to the 19th giga-electron-volts. We are 15 orders of magnitude short. An alternative approach: loop quantum gravity. Rather than starting with strings in spacetime, loop quantum gravity quantizes spacetime itself. Space is not continuous, but granular, composed of discrete units at the Planck scale. These are represented mathematically as spin networks, nodes connected by links, each carrying quantized geometric information. As spin networks evolve, they form spin foams, a quantum history of spacetime geometry. When applied to cosmology, loop quantum gravity suggests the Big Bang singularity is replaced by a quantum bounce. As the universe contracts toward Planck density, quantum geometric effects create a repulsive force. Collapse halts. Expansion begins. The theory predicts a maximum density below the Planck density. The universe rebounds before infinite compression. This opens the possibility of a cyclic cosmos. Expansion, contraction, bounce, expansion again, potentially without beginning or end. But like string theory, loop quantum gravity lacks experimental confirmation. The predictions lie beyond current observational reach. Quantum cosmology takes a different approach entirely. Rather than treating the universe as a classical object evolving in time, it applies quantum mechanics to the cosmos as a whole. James Hartle and Stephen Hawking proposed that the universe has no temporal boundary in the past. By using imaginary time, a mathematical technique from quantum field theory, the Big Bang singularity smooths into a gentle curvature, analogous to the South Pole on Earth. There is no edge, no beginning, just continuous geometry. This proposal is model-dependent and not universally accepted. It relies on specific assumptions about quantum gravity and the application of path integrals to cosmology. Different theoretical frameworks yield different conclusions about cosmic origins. The mathematical foundation is the Wheeler-DeWitt equation, which describes the quantum state of the entire cosmos, but solving this equation is extraordinarily difficult. Interpretation remains contentious. Alexander Vilenkin proposed an alternative, quantum tunneling from nothing. The universe does not evolve from a prior state. It emerges probabilistically from a quantum vacuum, a transition without classical antecedent. These are not empirical claims. They are attempts to extend quantum mechanics into a regime where spacetime itself is subject to uncertainty. Another candidate: asymptotic safety. This approach seeks to make gravity renormalizable, quantum mechanically consistent by allowing the gravitational coupling constant to become scale invariant at high energies. If successful, general relativity might be a low-energy approximation of a more fundamental quantum field theory of gravity. Work continues. The mathematics is complex, results are incomplete. All of these theories are mathematically sophisticated. All attempt to resolve the breakdown at the Planck scale. None have been tested. A question lingers beneath all of this. What does before mean if time itself emerges near the Planck scale? If general relativity and quantum mechanics together suggest that classical spacetime is not fundamental, that it arises from deeper quantum structures, then time may not extend arbitrarily into the past. This is a theoretical proposal, not an established fact. The question, what happened before the Big Bang, might resemble asking what lies north of the North Pole, though this analogy depends on accepting specific models of quantum cosmology. Not a failure of knowledge, a failure of the question itself. This is not metaphysics. It is a logical consequence of treating time as a physical parameter subject to quantum uncertainty within certain theoretical frameworks. We do not know if this is true, but it is possible. And if it is, the nature of cosmic origin shifts fundamentally. Theory without observation remains mathematics. The Planck epoch may lie beyond current instruments, but not necessarily beyond future ones. If inflation occurred, it produced gravitational waves. These waves would have stretched to cosmic scales, leaving imprints in the polarization of the microwave background. Specifically, a pattern called B-modes, a curl-like structure in polarization distinct from density fluctuations. Detecting these would provide direct evidence of inflation, and because the amplitude of the signal depends on the energy scale of inflation, it could constrain Planck epoch physics. Multiple experiments are underway or in development. The Simons Observatory in Chile, Lightbird, a planned Japanese satellite, CMB Stage 4, a network of ground-based telescopes designed for unprecedented sensitivity. The challenge is separation of signal from noise. Galactic dust produces polarization patterns that mimic primordial B-modes. Systematic errors must be controlled to extraordinary precision. Beyond the microwave background, gravitational wave astronomy offers another window. The Laser Interferometer Space Antenna, LISA, will detect gravitational waves at frequencies inaccessible to ground-based detectors. If phase transitions in the early universe produced gravitational waves, LISA might detect them. Some theoretical models predict subtle deviations in particle behavior at high energies, quantum gravity corrections to the standard model. Ultra-high-energy cosmic rays, neutrino oscillations, or anomalies in gamma-ray bursts could carry signatures of Planck scale physics. Particle accelerators will never reach Planck energies directly. The energy required exceeds anything technologically feasible. But indirect effects, modifications to scattering cross-sections, decay rates, or symmetry-breaking patterns, might appear at lower energies if quantum gravity influences the vacuum structure. The observational frontier is real. The Planck epoch is not beyond physics. It is beyond current instrumentation. And instrumentation improves. We may, possibly, be able to test elements of Planck scale cosmology. Not directly, but indirectly, through secondary signatures imprinted on observable quantities. Whether that will resolve the boundary or simply refine our description of it remains to be seen. One mystery threads through all of this: entropy. The second law of thermodynamics states that entropy, disorder, increases over time. Isolated systems evolve toward equilibrium, energy disperses, structure degrades. But the early universe was extraordinarily low in entropy. Matter and energy were distributed with near-perfect uniformity. Tiny fluctuations, 1 part in 100,000, provided the seeds for galaxies. This initial smoothness represents a very special, very unlikely configuration. Statistically, high-entropy states are overwhelmingly more probable. The universe should have begun in thermal equilibrium, not far from it. Why didn't it? Roger Penrose calculated the probability of the universe beginning in such a low-entropy state by chance given certain assumptions about phase space and initial conditions. The odds? 1 in 10 to the power 10 to the 123rd. A number so incomprehensibly small it defies intuition. This estimate depends on specific theoretical frameworks and is not universally agreed upon as the definitive measure of cosmic fine-tuning. Inflation does not fully solve this. While inflation flattens space and dilutes defects, it requires its own low-entropy initial conditions, a homogeneous inflaton field in a false vacuum state. The problem is pushed back, not eliminated. And this connects to the arrow of time itself. Thermodynamic processes are irreversible because entropy increases. We remember the past, not the future, because memory formation is an entropy-increasing process. The direction of time is statistical, but if the early universe began in a low-entropy state, the arrow of time emerges from cosmology. The past is different from the future because the Big Bang was different from equilibrium. Why was the Big Bang low in entropy? We do not know. It may be the deepest, unresolved question in cosmology, one that links the largest scales, cosmic expansion, with the smallest, quantum gravity and the Planck epoch. The boundary persists. We began with certainty. The universe is expanding. We have measured the rate with increasing precision, mapped the structure, decoded the chemistry of the first 3 minutes. We have photographed the oldest light in existence, radiation released 380,000 years after expansion began. We understand galaxy formation, stellar nucleosynthesis, recombination, Big Bang nucleosynthesis. We can model the universe back to 1 second with substantial confidence. We have a leading framework, inflation, that addresses large-scale uniformity in structure, strong theoretical support, indirect observational consistency, no direct confirmation. And then, at approximately 10 to the minus 44 seconds, our current physical frameworks reach their limit. Not because reality becomes infinite, not because causality breaks down, but because general relativity and quantum mechanics cannot yet be reconciled. Theories exist, loop quantum gravity, string theory, quantum cosmology, all mathematically sophisticated, all untested at the relevant scales. Observational windows are opening, primordial gravitational waves, high-precision CMB polarization, indirect quantum gravity signatures. We may, possibly, probe the Planck epoch indirectly, or we may find that some boundaries require fundamentally new physics to transcend. Throughout history, limits have receded when deeper theories emerged. The ultraviolet catastrophe dissolved with quantum mechanics. Mercury's orbit was explained by general relativity. The horizon problem found a possible answer in inflation. Will quantum gravity follow the same pattern? Will the Planck wall dissolve into a more fundamental framework? We do not know. What we do know is this: the universe can be understood. Not completely, not yet, but with extraordinary precision, back to a fraction of a second after expansion began. The boundary marks the edge of our current understanding. Whether it is permanent or provisional remains an open question. The first fraction of a second is not darkness, it is not mystery. It is a frontier where mathematics meets the limits of our present knowledge.